Hi, AP Chemistry. We're going to talk about the 3 ways to calculate G, just so we're all clear and square. And this is actually the end of chapter 17. So after we're done with this, then we just have practice in front of us and we will be ready to test our skills. Okay, so 3 ways to calculate delta G. All right, so the first way is via the equation that we have been talking about. Oh, wait for it. Here we go. So here's our equation. Remember, it relates free energy. It relates the enthalpy of the system, and then it also relates the entropy change. And remember, this is entropy of the system. It's not labeled, it has no subscript, and so you're automatically going to assume that it's of the system. And then, of course, we have a temperature too. So they give you delta H, they give you delta S, they give you the temperature. This would be a good time to pause your video, go ahead, do this calculation, and then come back to check your work against ours. All right, so the first thing I notice here is that my H is in kilojoules and my delta S is in joules per Kelvin. So we definitely want those to agree. Let's go ahead. I guess we'll just convert joules per Kelvin into kilograms. So I have joules per Kelvin. I want to get rid of joules, get it into kilojoules. So for every 1 kilojoule, there's 1,000 joules. Oops, I didn't mean to cross that off. Let me rewrite my units. All right, so joules is going to reduce out of there, and I'll have point. Okay, and then I'll have this. All right, so now we can just kind of plug and chug since we're solving for delta G, and that's what we have anyway. All right, also notice that my units are in Kelvin here and Celsius here, so I'm going to have to change that. All right, so notice I have Kelvin here and Kelvin here. Those are going to reduce out. So let's see. All right, and my answer is going to come out to be negative 394.3, but they only give us 3 sig figs up here, so I'll keep it to 394, and that's in kilojoules. Okay, so that's going to be our answer. There is our free energy change for the reaction specified. Notice that it's a negative free energy change, which means that this is going to be a spontaneous process. A couple other things on here. This would be a good time to go through and just double check. Force yourself through thinking about the signs of the numbers that they give you and telling yourself what the signs of those numbers mean. Another good thing to do here is check in with this term driving force. So the College Board this is one of the ways that they ask questions without giving you, like requiring you to actually do the calculation completely. They'll give you all this information. Delta H is this, delta S is this. The free energy answer comes out to be this. What's your driving force? And basically what they're asking you when they ask you what your driving force is which of these two terms is responsible for the outcome. So notice that delta H is negative. That's going to influence the delta G to also be negative. It's going to drive it in a negative direction. So our delta H value here is going to drive free energy in a spontaneous direction. Delta S is over here. Delta S is positive. But notice that the entire term is negative. So a positive delta S combined with a negative for the whole term is going to be negative overall. So delta S is also driving free energy in a spontaneous direction. So if they asked you what the driving force for this reaction would be, the answer would be it's both. Both enthalpy and entropy are influencing free energy in the negative direction, which is the spontaneous direction. So they're both driving forces since our delta G ended up being negative. Sometimes if your delta G ends up being one sign, the driving force is going to be the one who has the sign that matches the delta G sign. So if your delta G comes out to be negative, it's whichever one is driving in the negative direction. If your delta G comes out to be positive, it's whichever term drives the delta G in that positive reaction. So basically this driving force is the term, and you're deciding your two possible terms are the delta H term or this entire delta S times a negative T term. So whichever term matches the sign that your free energy comes out to be, that's your driving force. Okay, here is another example, and they ask you to calculate delta H, delta S, and delta G using the following data. Now this one, you can do a couple different ways. So why don't you pause the video, try it, and then come back and match up to what we do. All right, they do give you all values of delta G. So you can calculate delta G all by yourself. They also give you all the values for delta S, so you can calculate delta S just with the given information. Now they don't give you any values for delta H, and so in order to solve for delta H, you need to use delta S and delta G together. To solve for delta H. Remember, this is entropy of the system. Since they don't give you a subscript, it's automatically entropy of the system. So this is a new way of calculating delta G that we haven't seen before. It's basically the Hess's law version, because free energy is pathway dependent. It's a state function, so it's pathway independent. It's also an extensive property. So we find that all three of these thermodynamic criteria or thermodynamic variables, enthalpy, entropy, and free energy, they're all state functions. They're all extensive properties. And so you can solve for all of them in a Hess's law kind of way. Hess's law technically is referring to the use of enthalpy, but you can also use it for entropy and free energy. So this is our second way to solve for free energy. In order to do that, we're going to have to use the overall delta G change is going to be the sum of the free energy change for the products multiplied by their molar coefficients minus the sum of the free energy change for the reactants multiplied by their molar coefficients. Again, just like enthalpy of formation the entropy values and the free energy values listed at the end of the book in the appendix, they are for a reaction where the substance listed is the product. So that's why you need that negative symbol here if you're going to list it as a reactant. You have to flip the sign, right? Okay, so here we go. Let's do delta G. So 2 times the product, SO3, negative 396, minus your reactants. So 2 times SO2, which is negative 297, plus 1 oxygen times its entropy, which is 0. The delta G comes out to be negative 198. And that is in kilojoules. We have multiplied off the moles. Okay, now let's look at delta S. Similar idea. So product SO3 is 257 minus all the reactants. So we have 2 times 2 SO2, which is 248, plus 1 times oxygen, which is 205. Okay, and we can calculate an answer out there. All right, here we get a negative 187, and that's in joules per Kelvin, and we have multiplied off the mole. So let's go ahead and convert that into kilojoules. So negative 0.187 kilojoules per Kelvin. Okay, so now we can plug these values into this above, and if we solve for H, we're going to get delta G plus T delta S equals delta H. So we're going to take our G, negative 198 kilojoules, plus temperature is 25 degrees Celsius, so 298 Kelvin, times S, which is negative 0.187 kilojoules per Kelvin. Kelvin's going to reduce out. Delta H is going to equal I got negative 253.726. So let's round that off to 3 sig figs. So negative 254, and that's going to be in kilojoules. There we go. Okay, so here we see our second way of calculating free energy using a Hess's law sort of approach. And then we see that equation we just used on the last one, that method number 1 of calculating delta G in order to get back to H. So this is a 2 equation kind of problem. Look at us go. Okay, so free energy, like we talked about, is a state function. So Another way, all right, timeout. The way that we just used is using the free energy of formation. So technically that second way we just used, we have it listed here in the slides as number 1, using the enthalpy of free energy of formation. Remember, written as if all of these things were products. So if you use them as reactants, you have to flip the sign. You also have to multiply by coefficients. So this one, they're asking you to calculate free energy of formation of glucose. They do have the entropy of formation reaction here. I'm not sure why I have that. If we're calculating free energy of formation, we should have this whole equation in terms of free energy, right? Okay, anyway, in order to do it this way, we're going to have to look up all of these things in our appendix in the back of the book. And actually, this would be a good one to go through and do together as a class, since we just did one using the free energy of formation on that last example. So we'll go through and do this one together as a class. Is this a different one? Oh, well, we have 2 examples. We can do them both. Let's do it. Okay, so this is our last way to calculate delta G. So notice it is using free energy as a state function, but instead of using the free energies of formation in the back of the book, what we have to use here are the reactions. So this is the idea where we use reactions we have to back build a reaction that we want. So why don't you pause the video here, try this, and then come back and see how we do it together. All right, so like the other ones, we basically just have to look for what we want and then flip and multiply reactions to get that. So I'm just gonna go molecule by molecule by molecule. So the first molecule is carbon monoxide, and I'm gonna look through these reactions to see where I find carbon monoxide. And the only way I see it is there. Now I want it as a reactant. It's given to me as a product, so I need to flip this reaction. I also want 2 carbon monoxides, and the reaction does give me 2, so I don't have to multiply it. So every time you do this, you're going to make 2 or 3, I guess, qualifications. You're going to look for the molecule you want. The second thing you're going to do is flip if necessary. Is it a reactant? Well, is it given to you as a reactant or as a product? If it's given to you in the form that you want, you don't have to flip it. If it's given to you in the opposite form, then you do have to flip it. All right, and then the third one, you need to look to see if you need to multiply. And this is done by looking at coefficients. What's the coefficient you want? What's the coefficient you're given? If they match, you don't have to do anything. If they don't match, you have to multiply the given one to get what you want. All right, so in this first reaction, we're going to flip it to CO. I'm going to skip states for now. 4H2O. All my waters are in gas. My carbon monoxides are in gas. My carbon dioxides are in gas. Okay, so my states are good. Goes to 2CH4 plus 3O2. Since I flipped the reaction, I have to flip the delta G. So positive 1088 kilojoules. Since I didn't multiply it, I'm not going to multiply delta G. All right, oxygen is actually in both. So I'm going to skip oxygen and just hope that it works itself out. Let's see if I'm right about that. All right, carbon dioxide is here. So I want it as a product. It is currently a product. I do not have to flip it. I want 2 of them. I currently have 1 of them. I do have to multiply it. So I'm going to multiply everything by 2. So 2CH4, 4O2, 2CO2, 4H2O. So the delta G does not need to be flipped, but it does need to be multiplied by 2. All right, now I can double check that I did this right by adding up my 2 reactions. And then once I know that I did it right, I can add up my free responses. Okay, so carbon monoxide shows up here and it doesn't show up anywhere else. So 2CO. Water shows up here and also here. So water is going to reduce itself out. Methane shows up here, 2-methane. It also shows up here as 2-methane, so that's going to reduce itself out. Oxygen, I have 3 oxygen here. I have 4 oxygen here, so that's going to reduce itself out, but leave 1. So plus 1 O2. All right, so I did this, I did this. Now I am left with carbon dioxide here, but that doesn't show up anywhere else. So 2CO2. And I have gotten the reaction that I'm looking for. That's a good sign. So now I can just add up the free energies. 1088 plus 2 times a negative 801. So I'm going to get a delta G of the reaction equal to negative 514, and that is in kilojoules. It gave me 4 sig figs, so I can keep 3 sig figs. Okay. Negative 514 kilojoules. Okay, this reaction is going to be spontaneous. Good to know. All right, so we have covered the 3 ways to calculate delta G. Let's go back and recap. I can use this first equation to calculate delta G as long as I have H's, as long as I have change in enthalpies and change in entropies. I may have to find some of the changes in entropies and enthalpies in order to use that equation, but I can do that. I can add up reactions, manipulate the reactions and add them up in order to get an overall reaction. And I can use free energies of formation, which is this equation only in free energy instead of entropy, in order to get the free energy of formation of a reaction. Okay, 3 ways to calculate delta G. Definitely try some of these homework problems. Go online, find additional practice problems if you need more repetition. Come to me with questions. We'll do some practice together in class, and then we are good to go on chapter 17. Let me know what questions you have, and I'll see you in class.